Hello everyone, welcome back to the DSA series. Today we are gonna be learning about the insertion sort algorithm. So guys, here we have an array of unsorted values 9, 12, 4, 10, 1, 5. So insertion sort guys will begin at our second index within our array. In this case it is index 1. We'll have a variable called current which will temporarily hold values at our current position. So in this case, we'll take whatever value is within our current position. In this case, it was 12, and we'll move it to our variable called current. Now guys, we'll compare whatever values are to the left. And if they are greater than whatever is in our current, then we will shift them to the right. If that is not the case, we will stop and we'll insert it into the position that is empty or has space available. So here guys, we'll start by checking if 9 is greater than our current. In this case, it is false. So therefore, we will not move any further. We'll take whatever is in our current and we'll move it back to its original position. In this case, it is 1. Now guys, we'll move on to the next iteration. So here we're at index 2. We'll take whatever value is in our current position. In this case, it is 4. We'll move it to our current variable. Now we'll examine the elements to the left and we'll compare it with whatever is in our current. So we'll say, is 12 greater than our current value? True. Then shift 12 to the right. So we shift 12 to the right. So now guys, we have one more value remaining on the left hand side of our array. So we'll compare 9 with our current value 4. So we'll say, is 9 greater than our current? True. So we'll shift 9 to the right since it is greater than our current. Now guys, we have an empty slot. So since we have no more values remaining to the left, we'll take whatever value is in current and move it at the empty position. In this case, it is at position 0. So 4 goes in to this empty slot. Now guys, we move on to the next iteration. So we'll take whatever is in index position 3 and we'll place it within our current. So our current is now equal to the value 10. Now we'll compare whatever values are to the left with our current value 10. So we'll say, is 12 greater than our current? True. Then shift it to the right. So we'll shift 12 to the right. So now guys, 12 is shifted to the right. So we will compare the rest of the values to our current value 10. So we'll say, is 9 greater than our current? False, because 9 is not greater than 10. So we'll stop and we'll place it at the empty position that doesn't contain any value. So we'll place current at position 2 since that is the only empty slot. So we'll take current and move it back to position 2. Now guys, we move on to the next iteration. Now we're at position 4. So we'll take the value that's in position 4, which is 1, and move it to our current. We'll compare the values to the left of our current. So we'll say, is 12 greater than our current? True. So in that case, we will shift it to the right. So you can see we're shifting 12 to the right. Now guys, we still have values remaining on the left hand side. So we'll compare the remaining values, so we'll say is 10 greater than our current? True. Then shift 10 to the right. So we'll shift 10 to the right. So now guys, we still have remaining values. We'll continue doing this. Is 9 greater than our current? True. Shift 9 to the right. So now we have shifted 9 to the right, and we have one more value remaining on the left. So we'll say is 4 greater than our current? True, because 4 is greater than 1. So we'll shift 4 to the right. So now guys, we have a empty position. So we'll take whatever is in current and we'll place it at this empty position. So current, so 0 now has the value 1. Now guys, we'll move on to the fifth and last iteration. So we'll take the value that's at position 5 and we'll place it within our current variable. Now guys, we will compare the values to the left. So we'll say is 12 greater than our current value? True, because 12 is greater than 5, so we'll shift 12 to the right. Now guys, we still have values remaining, so we'll say is 10 greater than 5 or our current? True, so we'll shift 10 to the right. So now guys, we still have values remaining, so we'll say is 9 greater than our current? True. Then shift 9 to the right. So now guys, we still have one more value remaining, so we'll say is 4 greater than our current? False. So because that is false, we will stop our iteration. So we'll take whatever is in current and we'll place it within this empty slot or position. So now 5 is in that empty position. So now guys, our array is sorted. And that is how our insertion sort algorithm works. So now guys, let's move on to the implementation or coding of our insertion sort. Alright guys, so let's start implementing our insertion sort algorithm. So we'll start by declaring an integer array of some random unsorted values. Let's say 9, 5, 3, 1, 4, 12, 10, 7, 6, 8. And let's get the size of our array. So we'll say size t. Size is equal to the size of our array divided by the size of an int. And let's create a function to print out our array. So let's say void print array, and it will accept a int array and a size t size, which is the size of our array. And we'll iterate through each one of our elements. So we'll say for size ti equals 0 as less than our array size I plus plus, and then we'll do a printf mod d space array at index I, and then at the end of our loop we'll do a printf new line. And let's call our print array function. So let's say print array, and then we pass in the size of our array. So let's display our array now guys. So you can see our array has the elements 9, 5, 3, 1, 4, 12, 10, 7, 6, and 8. Let's label it by doing a printf above here. We'll say unsorted array colon new line, and let's do that. So you can see our unsorted array right here now guys. Now let's implement our insertion sort algorithm. So we'll start by declaring a void insertion sort, and it will accept a int array and a size t size, which will be the size of our array. Now guys, we'll start by iterating from our second element within our array. So we'll say for size ti is equal to 1. Notice it is 1, not 0. We'll say I is less than the size of our array, I++, and we'll get our current element at our current index. So we'll say int current is equal to array at index I. We'll then declare another variable, let's say size tj, and we'll set it equal to I, which is our current index. And we'll do a while loop, so we'll say while j is greater than 0 and our array at index j minus 1, which is our previous element before our current index, is greater than our current value. Then we will set array at index j equals to our previous value. So we'll set it equal to array at index j minus 1. And then we will decrement j. So j minus minus. And then at the end of our loop, we will set array at index j equal to our current. So that way we will shift it to the correct position. And let's test out our insertion sort function. So we'll call our insertion sort function, then we'll pass in our array, then the size of our array, and let's do a printf sorted array colon new line print underscore array size, and let's test out our insertion sort. So guys, you can see our insertion sort algorithm works. So here is our unsorted array: 9, 5, 3, 1, 4, 12, 10, 7, 6, and 8. And here is our sorted array: 1, 3, 4, 5, 6, 7, 8, 9, 10, and 12. And that is our insertion sort algorithm, guys. Let's say we wanted to sort in descending order. All we have to do is change this greater than sign right here. So this greater than sign right here to a less than sign. And let's test it out. And you'll see it sorts in descending order. Let's change this back to ascending order. Alright, and that is our insertion sort algorithm, guys. So our insertion sort algorithm compares elements to the left. It then shifts elements to the right to create space to insert a value. And that is why it's called insertion sort, guys. It has a time complexity of O(n squared, which is quadratic time. It is okay on small data sets, but on large data sets it's poor. It takes less steps than bubble sort. In the best case scenario, insertion sort can perform an O(n time complexity compared to selection sort, which is O(n squared. And it's generally preferred over bubble sort and selection sort, guys. And that is our insertion sort algorithm. So I'll leave the source code in the description and in the comments. And I hope you guys learned something valuable, and I'll see you in the next DSA episode.